much. And, it's a pleasure to be here. Been wonderful 2 weeks, and I hope that my talk is very connected to pretty much everything, and especially to Ben's discussion of smoothness. So it's mainly based, my talk will be mainly based on two works. One, a previous work with my wonderful collaborator, Yichen Hu, and on a work which will appear soon with Georgi Shuklin. In this talk, I want to discuss, I want to try to get some answers, and I want to propose these answers to you. The three questions I care about is, do we have a classifying space of invertible stabilizer Hamiltonians? What are the invertible stabilizer phases, and do they have an omega spectrum? So indeed, Kitaev's argument runs just fine for stabilizer Hamiltonians and stabilizer states, if not even better. And we should be able to, we expect some version of Kitaev's conjecture in that world. So my setup is I'm going to be using just a simple cubic lattice in d spatial dimensions. I will always assume translation invariance. And in order to talk about commuting projector Hamiltonians, I need to choose a group in the algebra of all operators. I need to choose some group that will span all operators. So, for example, Pauli group, but in some exotic cases, I will need more exotic groups. So, and a stabilizer Hamiltonian is obtained from a finite set of Pauli operators, so that by translations and possibly multiplications. And terms of the stabilizer Hamiltonian commute such that the group generated by terms in the stabilizer Hamiltonian, they generate an isotropic subgroup of the Pauli group. And we have a luxury here. So there are four equivalent conditions. Local topological order, well, it's pretty much defined as an absence of local symmetries, or you can think of it as the condition that all errors are detectable and correctable, therefore, and it's equivalent to a statement that our stabilizer group is coisotropic within the Pauli group. And it also implies the local unique ground state. And please beware, many statements I make, they are true and can be proven in the stabilizer world. I'm not sure about the general statements. And so we define Hamiltonians to be in the same phase if there is a finite depth quantum circuit. So there is a strictly locality preserving automorphism that transforms one to another, and moreover, this is a very specific automorphism that just build of simple gates. And again, in this world, we have a great luxury. So the Hamiltonian is invertible in the sense that it has the homotopy inverse. If and only if it can be created by a Clifford QCA, and a Clifford QCA is just automorphism. It's just a general automorphism of the algebra of observables that preserves locality strictly. Alternatively, this Hamiltonian has to have a unique ground state on infinite lattice as well as on compactified lattice on the torus. And one more very convenient for us, this is a homological invariant. These are topological charges that admit braiding, and they correspond to anyons. And in our case, if there are no anyons, so the Hamiltonian must be invertible. And yeah, I should thank Bo and Yang for telling me how to prove some of the directions here.
Excuse me.
Yes.
When you say H is invertible, do you mean the ground state for H is invertible at phase?
I mean both. Like there's an inverse to the Hamiltonian, and the yeah, these are equivalent to me.
It's invertible. If ground state has zero energy, then H is not invertible. So I'm confused.
Is what?
If ground state have a zero energy, then the H is not invertible.
Oh, no, not as an operator, not the spectrum of the operator, in a sense that, it's I can stack it with another Hamiltonian and then they're in the trivial phase in that sense.
Oh, I see.
Yeah, not in the, it's not that spectrum. So, all right, so how do we start thinking about Kitayev's conjecture for bosonic phases? So we have initial condition that invertible bosonic phases are their classifying space is simply CP infinity, which just means it's just an inclusion of ever increasing inclusion of complex projective planes with a chosen base point. And so if we need if we can to having this picture, we can already talk about continuous families of states, and we can talk about Berry curvature and so on. So that's basically one thing we know about Kitayev's conjecture to start with KZ2. I mean, classifying spaces. But what about stabilizer invertible phases? Well, they're still pure, but let me remind you that what stabilizer states are, and the example of qubit. So we have Pauli operators, and stabilizer state or stabilizer code is just eigenvector of eigenvalue 1 of x, y, or z. And there are exactly 3 of them in the case of a qubit, and in the case of a Q3, there will be 3, and that many, if I have n copies of qubits. So there is a problem here. It's a discrete set. What can there be any classifying space here? Well, we'll see. First of all, I want to introduce the symplectic machinery. That's a very convenient way to encode, to encode the Pauli group and Lagrangians, and that's all I care about. And Lagrangians, it's a Lagrangian subspaces. It's not and they'll be coming from Hamiltonians, but still not the same Lagrangians in the field theory. Right. So Lagrangian is just the isotropic and coisotropic subspace in the symplectic space that must split as a module. Right. So I just use these 3 vectors, and these are essentially just 3 different directions in the F2 projective plane, just the analog of a CP2, CP1. And well, I will do stabilization with copies of qubits, and I can consider a space of all Lagrangian subspaces in all in symplectic spaces of all dimension. All right. So we kind of obtain a set of stabilizer codes in copies of a qubit, a still discrete pointed set. Well, so this letter L I mentioned, in fact, it is in fact a functor. I mean, I can, instead of F2, I can insert any other ring, and it will give me a set of Lagrangians in symplectic spaces, in symplectic modules. So for a qubit, I'll use FP, and moreover, I can go in. I can do many body physics. I can just by replacing my simple prime field with a ring of Laurent polynomials. So the idea is that I just have I have just a qubit for each lattice side, and now I use this group ring ZD to label the sides. And again, so there is a very convenient theorem saying that invertible stabilizer states or stabilizer Hamiltonians are in one-to-one correspondence with the Lagrangian submodules over that ring. And then so I have this, if I evaluate my scheme on this ring, I'll get this set of all invertible stabilizer states.
Just, do you mean Lagrangian for symmetric or anti-symmetric?
Anti-symmetric, yes.
It didn't matter before on the previous slide.
Well, I mean, I kind of showed -1. Well, I agree. Yes, I agree. Very good. No, that's anti-symmetric. So yeah, I roughly have Pauli X and Pauli Z, they commute. So I have I mean, I care about their commutant. They don't commute, but I need a commutant. So something anti-symmetric. Sorry. Right. So I have a pointed set, and it's a scheme. Well, I could can put Zariski topology on it if if you like it, but you might not. So let me see. Let me say something more. So for any ring, I can introduce a ring of extended ring of polynomials with coefficients in R, and this ring automatically comes with 2 evaluation maps. So I can evaluate polynomials. Whatever ring is, I can evaluate these polynomials at 0 and 1. And I can, if I change rings, I have 2 maps between the categories of modules, and I can evaluate my Lagrangian Grassmannian L at these 2 points as well. So get 2 maps between these 2 Lagrangian Grassmannians. And as I said, the elements of L of R are invertible stabilizer Hamiltonians. So, and I say that the 2 points are in the same connected components if there is a Lagrangian over the extended ring that evaluates to my fixed points. Okay, so how does it work? Yeah, let's get back to the qubit. So as I mentioned, there are 3 Lagrangians, this vector, that vector, and that vector. And well, there's another nice feature that the symplectic group acts transitively on the space of Lagrangians. So all Lagrangians can be rotated to the standard Lagrangian, to the base point. And I choose base point to be 1, 0. And so these are symplectic matrices rotating them. And so I do a simple trick here. I just, instead of ones, of the diagonals, I insert t's. And in fact, these are the desired homotopies. So now if I evaluate them at 1, I'll get back my 3 Lagrangians. And if I evaluate it at 0, that's a homotopy to the base point. So in other words, pi 0, I mean, I defined pi 0 on 3 elements, and I'm able to construct them. Yeah, I mentioned this because, so first of all, the symplectic group has a physical meaning of Clifford QCA, and these special matrices that look like ones and on the diagonal and whatever of the diagonal, these are the so-called elementary symplectic matrices, and physically they correspond to Clifford circuits. So, right. Well, I mean, I can calculate now the connected components of all Lagrangians of the Lagrangian Grassmannian over in any dimension. Well, I mean, it works really good for p greater than 2. And yeah, as I showed in the example of qubit, it's very convenient to represent Lagrangians as to use the fact that it's a homogeneous space for a symplectic group. And we can calculate in that manner homotopy groups, and we get nothing up to spatial dimension 3. Well, that's roughly what we expected. We expect non-trivial QCA and non-trivial stabilizer phases in 3 dimensions. I don't want to specify what these groups are because I'll give the full answer later. Yeah, our main motivation to even run this algebraic machinery, because I didn't know how to prove any theorems about loops of Clifford circuits. So a Clifford circuit is essentially, well, a finite depth Clifford circuit. It's a brick wall, and bricks are made of Clifford unitaries. So it's a very, very discrete subset of all circuits, and not mentioning all automorphism of the algebra of local observables. And if I have a loop, that's totally not clear what are the homotopies of such discrete objects. But these definitions surprisingly worked. And yeah, we can study loops as just these time-dependent modules that start and end at the same base point. And homotopy class and homotopies of loops are just surfaces interpolating between loops. And so surprisingly, at least if we don't do qubits, really, everything works. And we have this omega spectrum-like relation. All right. So that's my answer, whether you like it or not, to the question, is there a classifying space of invertible stabilizer Hamiltonians? Right. So yeah, I mentioned this p dependence, and I'll have a list for different p's, which is going to be different. That's really ugly, and it's really not nice. And like what I was doing before, I was stabilizing prime qubits, like qubits of dimension 2 with qubits of dimension 2. I couldn't even add 4-dimensional qubit. Like I really had to care about my Hilbert space. I couldn't even do. So it could turn out that Hilbert spaces of the same dimension are not even isomorphic. That's nonsense. So we can get rid of that. So yeah. So for any Hilbert space, we parameterize with we present it as a group ring for a finite abelian group of the corresponding order. And there's a nice orthonormal basis of labeled by the group elements. And we can define generalized x and z. So x just acts by left multiplication, and z acts by a phase. So coming from the Pontryagin dual of the finite abelian group, which is isomorphic to D itself, of course. And generalized Pauli group is just it's generated by x is generalized z and the phase. So and we can consider this group on the lattice, but yeah, unfortunately, as I mentioned, we need sometimes we need more exotic Pauli groups, or we need more exotic bases or local operators. So the most general Pauli module that we care about, it's defined by resolvent. Sorry, it's defined by resolution with well, luckily 3 modules, but they, yeah, that's a luxury here too. So we just say, that it's resolved by these 3 modules, and it's purely torsion. And it's, well, its coefficients are pure torsion. So when I tensor with Q this short exact sequence, I'm getting a isomorphism between. So that's a condition on the generating map here. And well, it might look ugly, but we prove that any such module is a finite extension of d of zd. So, and a very generalized Pauli group is just m plus m dual. It's pretty much like I had it before, f2 plus f2, where second f2 is dual, and here it's the same thing. All right, so yeah, so we use these L groups, and we secretly used them before when we calculated homotopy groups of the Lagrangian Grassmannian. So these L groups are all about geometry of Lagrangians, how complex my Lagrangian coming from the Hamiltonian, how difficult it is to rotate it to the standard Lagrangian. And yeah, so these L groups we pretty much know, and these L groups themselves are not very physical, but the co-fiber appearing here is what we need. So roughly, like we have Z modules that must become trivial when we localize to Q, and in this stable homotopy business, there are no kernels; there are only co-fibers. So weirdly enough, we get in what we need here. And so these L groups are homotopy groups of the so-called L theory. And for good enough rings, we have this relation. So add in one spatial dimension, like lowers our homotopy groups. And that's, if you think about it, that's what we want from omega spectrum related to the Kitaev's conjecture. And here's the answer that we calculated. So the first column, so we get in nothing up to dimension 3, and in dimension 3 we get in this width group of pointed braided fusion categories, also known, this width group is also known as the width group of finite quadratic forms on finite abelian groups. And then we get in something in Z2, and then it repeats 4 periodically. It's not like I couldn't write, I can continue. And it should be compared, because that's the closest in spirit to the commuting projector phases as of Theo and Davide, and except they, they predict the full width group here, and I think we could get it too if we just considered lattices not only of spins but on fusion, so-called fusion lattices. Right. So this object we all know and love. And so essentially what we did, we confirmed what's already found. So we found that we proved that the examples found already are complete. So that's a complete set. So this 3D QCA/phases were found in that beautiful collaboration. And this phase with the Z2 gravitational anomaly was found by Lucas, Zhongwan, and Matt, Yuan, and Poshen. And this 0 is actually non-trivial, because if we did prime qubits, there would be something here. But amazingly, when you allow mixed qubits of mixed dimension, it vanishes. So some QCA becomes really a circuit. So that's a surprise. So this is the classification of invertible stabilizer phases, at least in lattices of spins. And finally, well, we already used homotopy groups of L theory and evaluated on a very simple ring. I mean, I can imagine evaluating on more general things than tori, maybe toric varieties at least. So by naturality, we propose that this L theory gives us the right spectrum of phases. And so this is the spectrum that will give us the homotopy groups that I presented on the previous slide. And here I voluntarily took the co-connective cover, so I killed all positive homotopy groups, because I don't want anything in negative spatial dimensions. But even if I calculated something in -2, I wouldn't get anything, just in case. And yeah, and so like we have our spectrum, we have its homotopy groups. We want to know how does it look like as a plain sequence of topological spaces. And the first thing, the stupidest thing we can write down, turns out to be correct. So this spectrum is so simple that it's really the generalized Eilenberg-MacLane spectrum. And this is easy to see because, well, easy to prove because the homotopy groups just have only 2 torsion, and this spectrum is a MSO module. So so it's really just an Eilenberg-MacLane spectrum. And yeah, so if that's our classifying spaces as of a generalized cohomology theory, and you can continue. And yeah, that's the answer for the third question. And yeah, so that's it.